Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe the channel. So today we're going to talk about the properties of the Orthocenter. Before we start, you may already notice that in the Chinese version of the properties of the Orthocenter, I actually split the videos into like three. Just because I stuck somewhere when I do the discussion of the properties, and hopefully we can have a smooth discussion in English version, and because in the Chinese version it was about more than 3 hours of the discussion, so let's see how can we discuss here. Okay, the first thing that we want to do is to define the Orthocenter, right? Orthocenter is a concurrent point of 3 altitudes in a triangle. And let me just draw the figure here. Let's say our triangle is ABC as I draw here. So this is DEF. We want to prove that BEAD and CF are concurrent. So because angle BAC plus angle ABE equals to angle BAC plus angle ACF equals to 90 degree, right? Because this is 90 degree, this is 90 degree, so this one plus this one equals to 90 degree, and this one plus this one equals to 90 degree. So we got that angle ABE equals to angle ACF, right? This one equals to this one, so call this as 1, this as 1. And similarly, we can find that if we call this as 2, this as 2, call this one as 3, this would be 3. And then we can use the angle form of converse Sivas theorem, right? Let's calculate for sine angle BAD to sine angle DAC times sine angle CBE to sine angle EBA times sine angle ABACF to sine angle FCB. We calculate for this one, right? If the production of these three terms equals to 1, that means we can use the converse Sivas theorem to say that AD, BE, CF are concurrent, right? And this one equals to sine angle BAD, that is sine angle 3, sine angle DAC, that is sine angle 2, sine angle CBE, that is sine angle 2, sine angle EBA, that is sine angle 1, and sine angle ACF, that is sine angle 1, sine angle FCB, that is sine angle 3, so it equals to 1, right? And now we know that AD, BE, CF are concurrent. And we call the concurrent point as H, which is a orthocenter here, right? We can name it as H. Okay, let's see the property 1. The orthocenter of a right triangle is at the right angle vertex. This is straightforward, right? Because when we want to get the orthocenter, we basically do the projection from each vertex to the opposite edge, right? So in a right triangle A, B, C, AB is the altitude of edge BC, and BC is the altitude of edge AB. And altitude AB and altitude BC meets on point B. which means that B is the orthocenter of the right triangle ABC. Okay, and the orthocenter of an acute triangle is inside the triangle. This is also straightforward because in an acute triangle, all the altitudes are inside of the triangle, which means that the orthocenter must be inside of the acute triangle. And for an obtuse triangle, the orthocenter is outside of the triangle. So we can start from a vertex which actually from the acute angle, and we do the projection. We do the projection for the opposite edge, right? And we know that the altitude is out of the triangle, which means that the orthocenter must be on this altitude, right? So altitude is out of the triangle. That means the orthocenter is out of the triangle in an obtuse triangle. Okay, now property 2. Let H be the orthocenter of triangle ABC. Then angle BHC equals to angle B. Here angle B means angle ABC, right? Plus angle C means angle ACB equals to 180 degree minus angle A. So for this one, it's very easy to see that angle BHC equals to 180 degree minus angle 2 minus angle 3. And angle 2 plus angle 3, that is angle BAC. So it equals to 180 degree minus angle BAC. Right? In the triangle ABC, 180 degree minus angle BAC, that equals to angle ABC plus angle ACB. Right? So we just prove this one. And for the other two, they're the same. Okay, now let's look at property 3. Let H be the orthocenter of triangle ABC. In HABC, any point is the orthocenter of the triangle with other 3 points as vertices. Such a set of 4 points is called an orthocentric set. The centers of circumcircles in an orthocentric set form another orthocentric set. 2 orthocentric sets are congruent. So for the property 3, we can split it into the first half and second half. The first half is saying that in HABC, any point is the orthocenter of the triangle with other 3 points as vertices, which means that H should be the orthocenter of triangle ABC, and C should be the orthocenter of triangle ABH. B should be the orthocenter of triangle AHC, and A should be the orthocenter of triangle BHC, right? So for H is the orthocenter of triangle ABC, that is obvious, and let's consider about the point C. So in the triangle ABH, we know that because BH is perpendicular with AE or AC, that means AC is the altitude of HBH. And because AD is perpendicular with BD, or AH is perpendicular with BD, that means BD is the altitude of edge AH. And we know that these two altitudes meet on point C, which makes C to be the orthocenter of triangle ABH. Right? It's same for the other 2 cases. So we just prove that the first half is true, that any point is the orthocenter of the triangle with other 3 points as vertices, right? And now we want to prove the second half. The second half is saying that the circumcenter in an orthocentric set, the circumcenters, right? The circumcenters, that means the circumcenter from the circumcenter for the triangle ABC, ABH, HBCH and AHC, right? It seems that the circumcenters in an orthocentric set form another orthocentric set. Two orthocentric sets are congruent. So let's prove that. The first thing that we just draw. Okay, we just draw the triangle and the orthocenter here, A, B, C. This point is H, right? And consider how can we find the circumcenter? We find the perpendicular bisector of edge BC here. And we find the perpendicular bisector of edge AB here. Right? So this should be the perpendicular bisector of edge AC. This is point O, and we want to find the circumcenter of triangle ABH, so we can find the perpendicular bisector of segment BH, right? So this is O1, this is O3, and if we do this, this is O2. Right? So we want to prove that O1, O2, O3 is congruent to the triangle ABC. Right, the first thing is that O1 is perpendicular with BC, and so let's call this point as D, this point as E, and this point as F, right? So O1 is perpendicular with BC, and AD is perpendicular with BC, right? So that is saying O1 is in parallel with AD. This one is in parallel with AD. Similarly, O3, O1 is perpendicular to BE, right? O3, O1 is perpendicular to BE. And BE also perpendicular with AC. So we know that O3, O1 is in parallel with AC. This one is in parallel with this one. And O3, O2 is perpendicular with AD. BC is perpendicular with AD. So we know that O3, O2 is in parallel with AD. In parallel with BC, right? O3, O2 in parallel with BC, because O3, O2 is perpendicular with AD, and O3, O2, AD is perpendicular with BC, so O3, O2 is in parallel with BC. And for O1, O2 is perpendicular to CF. AB is perpendicular to CF, right? This one is perpendicular to CF. And AB is perpendicular to CF. So we know that O1, O2 is in parallel with AB. Okay, based on these things, on the last three, we know that O3, O1 is in parallel with AC, O3, O2 is in parallel with BC, O1, O2 is in parallel with AB. That means triangle O1, O2, O3 is similar to triangle ABC. Right? It's similar to triangle ABC. And also because O1, O01 is in parallel with AD, O3, O1 is in parallel with AC, so that angle O3, O1, O equals to angle CAD. Or we can actually say, because O01 is perpendicular with BC, so and O3, O2 is in parallel with BC, so we know that O01 is perpendicular with O3, O2. And also because O03 is perpendicular with AB, CF is perpendicular with AB, so and also O1, O2 is in parallel with AB. That means O03 is perpendicular with AB, right? And these two are in parallel. So O03 is perpendicular to O1, O2. That means O is orthocenter of triangle O1, O2, O3, right? O is the orthocenter of triangle O1, O2, O3. Okay, now we want to prove that triangle ABC is congruent to triangle O1, O2, O3. So before we do that, we have to prove another. We have to let me show here. We have to prove something else. Okay, so it's actually it's another property we will discuss later. But I think that if we play it in advance, then this proof would be straightforward. So think about triangle ABC here. Right, think about the triangle ABC, and we find the orthocenter here. We extend AD, so this is H. We extend AD to a point, let's call it K. Right, if we connect BK, we connect CK. We know that angle KBC equals to angle KAC, right? This one equals to this one, because they all reference to the arc KC. And because angle BHD equals to angle AHE, right? This one equals to this one. And this is 90 degrees, this is 90 degrees, so we know that angle EAH equals to angle DBH, which means angle KBC equals to angle DBH, right? Angle KBC equals to angle DBH equals to this one. And for, look at arc BK, right? So angle BCK equals to angle BAK, right? They're all reference to the arc BK. This one equals to this one. And because this one equals to this one, so this one equals the angle FAH equals to angle HCD, right? So this one, these three are equal, right? We know that angle HCD now equals to angle KCD. So if you look at the triangle BHC and BKC, they have two triangles, they have two angles are equal, and they also have BC equals to BC. So the triangle BHC is congruent to triangle BKC, right? triangle BHC is congruent to triangle BKC. This is very important because we know that the circumcircle of triangle BKC is circle O, which is a circumcircle of triangle ABC. That is saying that triangle BHC has the same radius of circumcircle as triangle ABC, right? So the radius of circumcircle of triangle BHC and triangle ABC are equal. And similarly, we can just prove that for the triangle ABH and the triangle ACH, they all have the same radius of the circumcircle as the triangle ABC. Okay, they're all equal. Okay, which means in this problem, we know that O1B equals to O1C equals to O2C equals to O2A equals to O3A equals to O3B. Right, they're all equal. And equals to OA equals to OB equals to OC. Okay. Now we connect BO1, CO1, and connect AO2, CO2. Okay, so look at this angle. O1 is a circumcircle of triangle BHC, right? O1 is a center of the circumcircle of triangle BHC, right? That is saying that the arc BC reference to an angle should be equal to angle BAC because the circumcircle of triangle BHC is an equal circle to the circumcircle of triangle ABC, right? So the equal chord BC reference to the same circular angle BAC or maybe QC, okay? Q is on the circumcircle, Q is on the circle O1, right? Okay, so that is saying the angle BO1C is twice of angle BAC. So angle BO10 equals to angle BAC, right? This one equals to this one. Okay, this one equals to this one. And now think about these two lines, right? So So if we look at here, the similar thing, right? The AC, the angle, the circular angle reference to the AC should be equal in the circle O2 and circle O, which means angle AO2H should equals to angle ABC. Right? This one equals to this one. That is saying, because this one plus this one equals to 90 degrees, right? That means this angle equals to this angle, because this one plus this one equals to 90 degrees. So this one equals to this one. Let me just make. And we already know that BA is in parallel with O1, O2, right? BA is in parallel with O1, O2. This one is in parallel with this one. And we know that AD is in parallel with FO1. That means, see, this one, the AD is in parallel with FO1, and FO1 and O1, O2 is in parallel with AB. So that is saying angle FO1, O2, right, equals to angle DAB. Right, equals to angle DAB. So angle FO1, O2 we can represent for this angle X right here. Okay, now we look at the angle BAO2 and angle BO1, O2. You can see they are equal, right? Because angle BO1, O equals to angle BAC, and angle O1, O2 equals to angle CAO2. So we know that angle BO1, O2 equals to angle BAO2. Right. So that is saying, so think about that this angle can be equals to this angle. It can only happen when BO1 is in parallel with AO2, right? Because BA is in parallel with O1, O2. So that is saying BO1 is in parallel with AO2 and BA is in parallel with O1, O2, which means ABO1, O2 is a parallelogram. So AB equals to O1, O2. Now we just prove that triangle ABC is congruent to triangle O1, O2, O3. Right. Okay. That is property 3. Let's see property 4. Property 4. Let altitudes in triangle ABC be AD, BE, CF. So A, B, C, A, D, B, E, C, F. D, E, F are foot of altitudes for A, B, C, D, E, F. There are 6 cyclic quadrilaterals, right? 6 cyclic quadrilaterals. 3 sets, 4 in each. Similar triangles. And AH times HD equals to BH times HE equals to CH times HF, right? Okay, because CF is perpendicular with AB, AD is perpendicular with BC, this is 90 degrees, this is 90 degrees, and also BE perpendicular with AC, so this is 90 degrees. And because this is 90 degrees, this is 90 degrees, then we know that HFBD is a cyclic quadrilateral, right? And because this is 90 degrees, this is 90 degrees, so HDCE is a cyclic quadrilateral. This is 90 degrees, this is 90 degrees, so HEAF is a cyclic quadrilateral. And because this is 90 degrees, this is 90 degrees, so AFDC is a cyclic quadrilateral. And this is 90 degrees, this is 90 degrees, so BFEC is a cyclic quadrilateral, right? And this is 90 degrees, this is 90 degrees. That means AEDB is a cyclic quadrilateral. So totally we have 6 cyclic quadrilaterals, right? And because this angle equals to this angle equals to this angle, this angle equals to this angle, so we can get triangle AHE, okay, AHE is similar to triangle ACD, and it's also similar to triangle BHD, and similar to triangle BCE, right? That's one set, and this set is for these 2 angles. And for these 2 angles, we have triangle AHF similar to triangle ABD, similar to triangle CHD, similar to triangle CBE. Wait, no, CBF, right? CHD is similar to triangle CBF. Okay, that is this part. And for this part, we know that triangle BHF is similar to triangle BAE, similar to triangle CHE, similar to triangle CAF. Okay, so we have 3 sets and 4 in each similar triangles. That's a property. Oh, another. We want to prove that AH times HD equals to BH times HE equals to CH times HF. It's simple, right? Because we just use the triangle AHE and BHD. We know that AH to BH equals to HE to HD. So AH times HD equals to BH times HE. And we can use triangle BHF is similar to triangle CHE. We have BH to CH equals to HF to HE. So BH times HE equals to CH times HF, which also equals to H times HD, right? That's property 4. Let's see property 5. In triangle ABC, H is the orthocenter, BC equals to A, C equals to B, AB equals to C. R is the radius of circumcircle of triangle ABC. Then AH squared plus A squared equals to BH squared plus B squared equals to CH squared plus C squared. So yeah, this is a property that I wish audience can keep in your mind, that whenever we see an orthocenter in the figure, and we also see the circumcenter or circumcircle in the figure, the first thing we do is to find the proper vertex and connect it with the circumcenter and extend it to meet the circumcircle on a point. Let's call it A, B, C here, and this is D, this is E. So of course, let's call this point as F, right? We connect BO and extend it to meet the circumcircle of triangle ABC on point J, right? Now we connect JC, we connect AJ, right? Because angle BCJ, BJ is the diameter, so angle BCJ is 90 degrees, right? That means JC is perpendicular with BC, so AD is perpendicular with BC. That means AD is in parallel with JC, right? And because BJ is diameter, so we know that angle BAJ equals to 90 degrees, which means JA is perpendicular to AB. And we already know that CF is perpendicular to AB, right? So AJ is in parallel with CF. Now we know that AJ in parallel with CF or CH, and AD or AH is in parallel with JC. So we got AHCJ is a parallelogram, right? And with this, we know that AH equals to CJ. Therefore, AH squared plus A squared is BC squared equals to CJ squared plus BC squared equals to BJ squared equals to 2R squared, right? And it's similar for the BH plus B squared and CH plus C squared. They're all equal. Okay, that's property 5. And let's see property 6. Let R be the radius of the circumcircle of triangle ABC. AH equals to 2R times cosine A. So this would be straightforward once we have this figure here, right? Because AH equals to CJ, and angle BJC equals to angle BAC. So CJ equals to BJ times cosine angle BJC, which means AH equals to BJ, which is 2R, right? Times cosine angle BAC, which is cosine A. We have absolute notation here just because in the obtuse triangle, the cosine obtuse angle would be a negative number, and we're actually looking for the distance of 2 points, so that should be a positive number. Okay, that's it. That's property 6. And let's see property 7. H is a point on the plane of triangle ABC. H is the orthocenter of triangle ABC if and only if one of the following conditions is true, right? And we have several conditions here. We have actually 5 conditions here. We discuss each of them. Just give me 1 minute, I need to grab some water. Excuse me. I'm back. So, let's see. The symmetrical points of H to the 3 edges are all on the circumcircle of triangle ABC. So first thing that we just actually proved that if H is a orthocenter, we know that the symmetrical point, because we extend the AD to a point K here, then we just proved that triangle BHC is congruent to triangle BKC. Did we? Yeah, we did, right? BHC is congruent to triangle, triangle BHC is congruent to triangle BKC, right? That means HD equals to DK, which means K is a symmetrical point of H to HBC, okay? So let's look at the property. It seems that the symmetrical points of H to 3 edges are all on the circumcircle of triangle ABC. Okay, so if H is a orthocenter, then they're all on the circumcircle of triangle ABC. It's true, right? So now we want to prove that if that in triangle ABC, if we find a point H, the symmetrical point of this H to the 3 edges are all on the circumcircle of triangle ABC, right? This is ABC, and let's call this point as H1, this as H2, this one as H3. So H1 is a symmetrical point of H to BC, and H2 is a symmetrical point of H to AC, and H3 is a symmetrical point of H to AB. And accidentally, that H1, H2, H1, H2, H3 are all on the circumcircle of triangle ABC. So we want to prove that H should be the orthocenter. Okay, so we can do this. We connect HC. We connect H2C. We connect H1C. Right, because H1 and H1 is a symmetrical point of H to BC. So we know that HC equals to H1C. And because H2 is a symmetrical point of H to AC, That means HC equals to H2C, right? So the question is that how can we prove that AH is perpendicular to BC, right? Okay, now because H1C equals to H2C, that means the circular angle of H2C equals to the circular angle of H1C, which means angle H2AC equals to angle H1BC, right? And because H1 is the symmetrical point of H2BC, so HBC equals to angle H1BC, this one. So we already know this one equals to this one, and H1BC equals to angle HBC, right? And we also know that equals to HBC, this one, and H2AC, this one equals to angle CAH, or HAC. So this angle equals to this angle. Okay, so this one equals to this one. Now let's just, to simplify the calculation, now let's just give them a name. We call this as angle 1, right? So we can use a similar method on the HB, right? We use it on the HC because HB equals to H3B and equals to H1B, right? That means the circular angle of reference to the chord BH1 equals to the circular angle reference to the chord H3B, which means this angle, right? That is reference to the chord H3B equals to this angle. And we already know that this one equals to this one, and this one equals to this one. So let's give a name as 2, right? And also for the HA, we know that HA equals to H3A equals to H2A. That means the circular angle reference to HA, which is the angle ACH2, right? This one equals to the circular angle reference to H3A, that is this one. So this one equals to this one, and this one equals to this one. This one equals to this one. Let's call it 3. Okay. So now we can see that angle 1 plus angle 3 plus angle 2 plus angle 1 plus angle 3 plus angle 2, which means twice of angle 1 plus angle 2 plus angle 3 equals to 180 degree. So angle 1 plus angle 2 plus angle 3 equals to 90 degree, right? Then this angle, the angle BHH1 equals to 90 degree, because this is 90 degree, right? Minus angle 1 equals to angle 2 plus angle 3. Okay, so this angle equals to angle 2 plus angle 3. We already know that HH2 is perpendicular with AC, HH1 is perpendicular with BC. So we know that, let's call this point as D, this point as E, this point as F, right? We know that HDCE is a cyclic quadrilateral. Right? And we know that angle BHD equals to angle 2 plus angle 3 equals to angle ECD. Right? So this angle equals to this angle. That means EHB are collinear. So we got EHB are collinear, right? And because HE is perpendicular with AC, so we know that BE is perpendicular with AC, and H is on BE, right? So that is saying BHE is the altitude of edge AC, right? Similarly, we can get that AHD is altitude of edge BC, which means H is orthocenter. Okay, that's the first property 7, first set. And let's see the second one. Okay, this is the first condition. We just proved that. And for the second condition, the circumcircles of triangle ABC, ABH1, ACH1, sorry, ABC, ABH, ACH, and the triangle BCH are equal circles. We just proved that if H is orthocenter, that triangle BCH, triangle ACH, and the triangle ABH has a same radius of the circumcircle of triangle ABC. Right? We just proved that. So that means if H is the orthocenter, then this is valid. Now we want to prove that if triangle BHC, triangle AHB, and the triangle AHC, and the triangle ABC has the same radius of circumcircle, H should be the orthocenter. Sorry. Right? So we just proved that, so we want to prove the second part, that if triangle BHC, triangle AHB, triangle AHC, and triangle ABC have same radius of the circumcircle, then H should be the orthocenter. Right? That's the thing we want to prove now. let's think about it. What can we think of from the circumcircle? What can we think of from the circumcircle? If the circumcircle has if the circumcircle has the same radius, let me think. So if we have the same radius, okay, now I got it. So let's do this way. Think about this. We just draw the circumcircle of 1 here to be easy think of, right? Because triangle, the circumcircle of triangle ABC is an equal circle to the circumcircle of triangle BHC, right? That means if we that means the angle BHC, equals to 180 degree minus angle BAC, right? So let me redraw the figure, that's easier to explain. So we have this circle here, and we just actually we have the circle here, and we have the orthocenter here, right? Think about that. We have the equal circle, right? The radius are the same, so we have the equal circle for the circumcircle of triangle BHC and the triangle ABC, and H here. That means because we can find any point on the circle O1, right? Circle O1, this is circle O, C. So we can find any point on the circle O1, and we know that if we have a circular angle that, for example, BQC, because BC is a same chord in the circle O1 and circle O, so that the angle BQC equals to angle BAC, and angle BQC plus angle BHC equals to 180 degree, right? So that means angle BHC equals to 180 degree minus angle A. Right? Angle BHC equals to 180 degree minus angle A. Similarly, we got angle BHA equals to 180 degree minus angle C, and also angle CHA equals to 180 degree minus angle B. Right? Now let's think about this way. So we already know that A, B, C. We already know that if the Orthocenter H satisfy this condition, that angle BHC equals to 180 degree minus angle A, and angle BHA equals to 180 degree minus angle C, and angle CHA equals to 180 degree minus angle B, right? So that is saying if there exists another point, let's call it F, right? The point F also satisfies these three conditions. Think about that. The F also satisfies these three conditions. That means BFHC is a cyclic quadrilateral. AFHC is a cyclic quadrilateral, and ABFH is a cyclic quadrilateral, right? So for BCHF and AFHC, these two circles has three concurrent points. That is impossible, right? Two circles just have two maximum have two concurrent points. So that is saying F cannot be a different point to H, right? Which means F should be H, and this is only valid when H is when this point is the orthocenter of triangle ABC, right? Okay, that's a second condition. Let's see the third one. I think it's better to move it down a little bit. Okay, the third one is saying that the symmetrical point of H to the midpoint of three edges are all on the circumcircle of triangle ABC. Okay. Right, this is a midpoint, this is a midpoint, and this is a midpoint. So if we say this is a point H, right? And the symmetrical point of H to the midpoint of ABC, three edges of triangle ABC. So let's call it H1, and this one called M. This one called N, this one called P. So the symmetrical point of H, so here is H1, this one is H2, and this one is H3, right? They are all on the circumcircle of triangle ABC. Right, so we want to prove that H is orthocenter. So what we can get here is that if we connect the BH and BH1, also HC and CH1, right? Because BC and H1 bisect to each other, right? H and M is a midpoint, and so that BM equals to MC. H and H1 are symmetrical to point M, so HM equals to MH1, right? Which means BH1CH is a parallelogram. Right, this is a parallelogram. So triangle that means triangle BH1C is congruent to triangle CHB, right? Also means the distance from H to BC equals to H1 to BC, right? So equals to H1 to BC. So you can think of that. That means the symmetrical point of H to BC, right, has the same height of H1 to BC. This point is also on the circumcircle because right, the symmetrical point of this one is also on the circumcircle. Similarly to H2 and H3, we can prove that the symmetrical point of H to the AC and the symmetrical point of H to AB are all on the circumcircle, which we can use the first condition just to say that H is Orthocenter, so that all these points can be all on the circumcircle, right? I hope you get this. The main point here is that because HM equals to MH1, so this is parallelogram. That means the distance from H to BC equals to the distance from H1 to BC, right? And we can simply draw a parallel line to the BC to here, and we can easily prove that that point is a symmetrical point of H to BC, right? So that is saying that point is the symmetrical point is also on the circumcircle. So we use condition 1. We can prove that it's the H should be the orthocenter. Okay, let's see property 4. I mean condition 4. Condition 4 is saying that in A, B, C, D, E, F. Condition 4 is saying that angle HAB equals to angle H. Oh, we don't know this. Sorry. My bad. So we want to prove that. Okay, for the first half, that if H is an orthocenter, then of course angle HAB equals to angle HCB, right? Angle HAB equals to angle HCB, and angle HBC equals to angle HAC. Of course, that's true. Excuse me. Now we want to prove that if we just know that HAB equals to HCB. And we know HBC equals to HAC. Can we prove that H is Orthocenter? So for this problem, let me see. I think we can have several ways here. The first way is, excuse me. The first way is that let's just extend the AH here, right? And we can also extend the CH here and extend the BH here, right? Basically, we want to prove that these things are okay. See, because this angle equals to this angle, so we just extend AH to D, BH to E, CH to F. We want to prove that CF is perpendicular with AB, AD is perpendicular with BC, BH is perpendicular with AC, right? And we know that this angle equals to this angle. So A, B, D, E are cyclic, right? These are cyclic. And because this angle equals to this angle, let me actually do this here. Okay. So we know these are cyclic, right? Means so A, B, D, E are cyclic. That means angle BAD equals to angle BED, right? This one equals to this one. And we already know that angle BAD equals to angle HCB, right? That means the angle BED or HED equals to angle BHCD. So HEDC are cyclic. Right, these four points are cyclic. And will we have one second. Yeah, so this angle also equals to this angle, so AFDC are cyclic, right? I don't want to lose myself here. Just 1 second. We want to prove that this is perpendicular with this one, right? Okay, so what else we have here is that because this is cyclic and we know that this angle equals to this angle, so we know this angle equals to this angle, right? I mean AFDC are cyclic, so look at the chord DC. We got this angle equals to this angle, so we know that FHDB are cyclic. right? So let's see. Let's call this angle as angle 2, right? And this angle as angle 3. We already know that angle 2 plus angle 3 equals to 180 degree. So this is angle 2. Because A, B, D, E, this one, see, A, B, D, E are cyclic. So angle AEB equals to angle 2, right? So this is angle 2. And because HDCE are cyclic, so angle 2 equals to angle 3, right? HECD are cyclic, so angle 2 equals to angle 3, which means angle 2 equals to angle 3 equals to 90 degree, right? That means this is 90 degree, this is 90 degree. So BE is perpendicular with AC and AD is perpendicular with BC, right? That means H is also center. Okay, let's see the fifth condition. That BAO equals to, okay, let's just drop it here. Angle BAO, so this is O. Roughly say this is. So we know that BAO, this angle, equals to HAC, equals to HAC, and angle right, BAO equals to HAC, and angle ABO, ABO wait, is that correct? Just ABO, okay? Let's assume it's correct. ABO equals to HBC. Oh, yeah. And O is a circumcenter, right? We want to prove that H is an orthocenter. So let's see. This angle equals to this one. This angle equals to this one. And what else we have here? We want to prove that angle, actually we want to prove that, still we want to prove AH is perpendicular with BC and BH is perpendicular with AC, right? So angle BAO actually equals to angle ABO, right? I'm not sure why it... Okay, so that means these four angles are equal, right? And angle BAO can be rewritten as half of angle 180 minus angle AOB, right? And angle AOB, that is twice of angle C. So the angle BAO equals to angle ABO equals to 90 degree minus angle C, right? So that means this angle equals to 90 degree minus angle C, which means AH is perpendicular with BC, right? And actually this angle equals to this one, and this is C, so that means BH also perpendicular with AC. Okay, then H is orthocenter. Okay, now let's look at property 8. Property 8. In non-right triangles, a line passing through H meets AB, AC on PQ respectively. Then we have this one. Okay. Let's just draw a triangle here, and we find the orthocenter H. Actually, if you remember that in the incenter, in the circumcenter, in the centroid, we all have the similar problem set, right? Similar properties. That's a line passing through the particular center, and we have the similar form of the equation. That's actually the way we do the research, right? We find a particular property in one special or certain center, and we want to generalize it. We just apply it onto other centers. That's actually the idea of doing a research, right? We just borrow the idea from one condition to another. Okay, let's see here. We call it PQ, and this is H. So this is D, this is E, this is F, right? And we want to calculate for AB to AP tangent angle B plus AC to AQ tangent angle C equals to tangent angle A plus tangent angle B plus tangent angle C. So if you remember this kind of AB to AP times something plus AC to AQ times something, we've already used this kind of method in the centroid, right? The idea is that we connect the PD and QD. We calculate AD to AH, right? So AD to AH equals to the area of APDQ to the area of triangle APQ, right? And it equals to the area of triangle APD plus area of triangle AQD to the area of triangle APQ. See, we find the plus sign. And it equals to APD to triangle ABC and the area of AQD to the area of triangle ABC, and to the area of triangle APQ to the area of triangle ABC, right? And the area of triangle APD to the area of triangle ABC, APD to ABC, it equals to B. So we calculate for the APD to ABD first, and then calculate ABD to ABC, right? ABD to ABC, that is BD to BC times ABD to APD to ABD, that is AP to AB, right? And plus the area of AQD to area of triangle ABC, so that is the area of AQD to ADC and times ADC to ABC. ADC to ABC, that is DC to BC, and AQD to ACD is AQ to AC, right? And divided by, so AD to AH equals to, divided by triangle area of APQ to ABC, because for the triangle APQ we can calculate it as half of AP times AQ times the sine angle PAQ, and for the triangle ABC we can use half of AB times AC times sine angle BAC. So that the ratio would be AP times AQ to AB times AC. So this equation equals to AP to AB, they cancel each other, and we flip this one. So we got BD to BC times AC to AQ plus here we have AQ to AC, they cancel each other, and we flip this one. We got DC to BC times AB to AP, right? Now we think about AD, and we think about AH, right? Let's just move the ADAH to the right side of the equation. So we have 1 equals to AH to AD times BD to BC times AC to AQ plus AH to AD times DC to BC times AB to AP. Right? These two are kind of, similar because we have something on the one side and something on another side which has AC to AQ times something and AB to AP times something, right? That's kind of already close. So we're on the correct path. Now we think about AH, AD, BD, BC. See, AH, AD. It's difficult to get AH to AD, right? AH, AD, and BD, and BC. Think about the target. We want to use tangent B, tangent C, tangent A, right? And AD here to BD, AD to BD, or BD to AD. That is 1 over tangent B, right? So AH and BC must be associated. AH and BC. Oh, AH and BC, it's obvious, right? Because we already know that triangle AHE is similar to triangle BCE. So AH to BC, let's write it here. AH to BC equals to AE to BE, which is 1 over tangent angle A, right? And that's AH to BC, AH to BC, and BD to AD. BD to AD equals to, see, BD to AD. That's 1 over tangent angle B. And DC to AD. DC to AD. That's 1 over tangent C, right? Tangent angle C. And we can replace this into here. So we got 1 equals to 1 over AH to BC, that's 1 over tangent angle A. BD to AD, that's 1 over tangent angle C times AC to AQ. Wait, tangent angle B, right? BD to BC. BD to AD, this one. And plus AH to BC, so 1 over tangent angle A times DC to AD, here, 1 over tangent angle C times AB to AP, right? So we have AB to AP. We multiply tangent angle A, tangent angle B, tangent angle C on both sides. So AB to AP times tangent angle B plus AC to AQ times tangent angle C equals to tangent angle A times tangent angle B times tangent angle C. Okay. Now we look at the target. We want to prove that the left side of the equation are the same, but for the right side of the equation, the target is tangent angle A plus tangent angle B plus tangent angle C. But we have tangent angle A times tangent angle B times tangent angle C. So we want to prove that they are equal. And the boundary condition here is that angle A plus angle B plus angle C equals to 180 degree or equals to pi, right? So we want to prove that this, now we want to prove tangent angle A times tangent angle B times tangent angle C equals to tangent angle A plus tangent angle B plus tangent angle C, and the only condition is that angle A plus angle B plus angle C equals to pi, right? Okay, so for this one, the simplest way that I can think of is actually to use a complex number. So I hope that you may be familiar with Euler equation, which is e to the I pi, or actually e to the I theta equals to cosine theta plus I sine theta, right? You can consider about a complex circle, right? So this is a real axis, this is an imaginary axis, so we have a theta here, right? So that is cosine theta on the real part, and on the imaginary part, that's I times sine theta, right? Okay, so because e to the I pi equals to actually imaginary of the e to the I pi, right? That is cosine pi plus I times sine pi. Sine pi equals to 0. So this one equals to 0, right? So we can extend this one to be imaginary of e to the I. Pi can be replaced by angle A plus angle B plus angle C, right, equals to 0, which means imaginary of EI angle A times EI angle B times EI angle C equals to 0. Right, now we can replace the EIA to this one, so the imaginary part of cosine A plus I sine A times cosine B plus I sine B times cosine C plus I sine C equals to 0, right? Consider about how can we get the imaginary part? So for each term, we have a real plus imaginary. So if we choose imaginary here, we must choose real in here and here, right? Or if we choose imaginary here, we have to choose imaginary here, imaginary here. So three I times together, that's still imaginary part. So we have, if we choose this one here, sine A, right, times cosine B times cosine C. That's one imaginary parameter, and plus for this one, if we choose here, then this must be cosine A, sine B, and cosine C, plus if we choose I sine here, so we got cosine A times cosine B times sine C. And don't forget, we can choose all of them, and two of them, 2I times together, that's -1. So I have minus sign here, and I, because we are looking for the imaginary part, so we just look at the coefficient. The coefficient would be sine A times sine B times sine C, right? And we know that this is imaginary part coefficient. It should be 0. So we divide it by cosine B, cosine C, cosine A on the this equation. Then we can get tangent A plus tangent B plus tangent C equals to tangent A times tangent B times tangent C. Okay, we just got the proof. So that is property 8. Now let's look at the property 9. Property 9 is saying that the distance from any vertex to the orthocenter in a certain triangle equals to twice of the distance from the circumcenter to the opposite edge. Right? Let's just drop it here. Remember that I said when we see the orthocenter and we see the circumcircle, the first thing we should do is to find the proper right. This is O, this is D, E, F, and this is H, this is J. So we know that AH equals to CJ, right? We want to prove that the distance from any vertex to the orthocenter, right? Let's say AH, that's CJ, equals to twice of the distance from the circumcenter to the opposite edge. So basically, it seems that we find the distance from the circumcenter to this is a vertex we were looking for, right? The vertex to the orthocenter and the distance equals to CJ. This one should be twice of the distance from O to BC, right? Because the distance from O to BC is actually the distance from O to the midpoint of the BC, and we know that this OM should be perpendicular with BC, right? And we already know that CJ is perpendicular with BC. O is the midpoint of BJ, M is the midpoint of BC. So OM equals to half of JC, right? Which means JC is twice of the OM. So equals to half of AH. AH is twice of OM, right? We just prove it. And property 10. The sum of the distance from 3 vertices to the orthocenter equals to twice of the sum of radius of inscribed circle and circumcircle. Right? Basically, it's saying that AH plus BH plus CH equals to twice of R plus R. Right? Okay, just look at this one. We already proved that AH equals to twice of, let's call it D1 here, and let's call this distance, the distance from O to AC is D2, and the distance from O to AB is D3, right? So we already know that AH is twice of D1, right? So BH is twice of D2, and CH is twice of D3. We want to prove that this one equals to twice of R plus R. Basically, we want to prove D1 plus D2 plus D3 equals to R plus R. If you remember, we proved this before, right? In the properties of the circumcenter. I'll just do the quick proof here. So in previous proof that we actually use the term of the directional distance, right? So we use it we use it just because we also consider about the case of obtuse triangle, right? But here, let's just use this one here. I mean, it's still true for the directional distance, right? It's just a reminder for you for the proof, because we already did that. You can go back to see the circumcenter properties of the circumcenter video to check on this. But we basically already proved this, right? Based on this, let's see, because we already know that OM is perpendicular with BC, so we know that OMB to this point is cyclic quadrilateral, so we can use Ptolemy's theorem, right? That means D1 times half of AB plus D3 times half of BC equals to R times this one, half of AC, right? I'll just say it. So you can do it for this cyclic quadrilateral, and do it for this cyclic quadrilateral, do it for this cyclic quadrilateral, and add them together, right? And then use also consider the condition that that AB plus BC plus AC times R equals to twice of triangle ABC. Okay, and then you will figure it out. Okay, let's see the next property.